Hey everyone, welcome back to another lesson in Algebra 2. We're studying function theory. Today I want to talk about transformations of functions. We're going to go through it little by little, and we're going to discover what each parameter does. And then we're going to witness it using a graphing calculator, and then we're going to start applying these transformations, making generalizations. So let's take a look. I've got a graph here. It's defined on a domain from -4 to 4. And let's just fill in this table of values together, shall we? So we're used to making a graph from a table of values, but we can do it in reverse. -4, f of x would be the y value, which is in this case 0. At -2, the y value is 2. And then at 0, the y value is 4. At 2, the y value is 2, and the 4, the y value is 0. And the f of x is the y values. Of course, that's not all the x values in this function, but those are just a few key ones to use. And I want to use those to try and fill in a graph and a table of values for each of these transformations. All right, so I'm going to leave that. Okay, we're going to leave that. Oops. We're going to leave that table there so that we can look at it. Okay. I'm going to take this graph and I'm just going to put it over here. So this is going to represent the original function over here. Let me move that over there because I want us to be able to keep an eye on it. All right, that looks pretty good, right? Okay, so now what I want to do is I want to look at a graph and a table of values for this function. Okay, so I've got f of x equals x plus 4. Well, let's talk about what this equation transformation is. So y is equal to f of x plus 4. That means each of the f of x values, which are located here in this right-hand side of the table, are going to increase by 4. So instead of a 0, we'll have a 4. Instead of a -2, we'll have instead of a 2, we'll have a 6. Instead of a 4, we'll have an 8. And we'll have a 6, and then we'll have a 4. And let's graph what that would look like. -4 to 4, -2 to 6, 0 to 8, 2 to 6, and 4 to 4. And what we get is this same shape, but shifted up 4 units. All right, let's take a look at this one. Okay. Now this time the x values are going to be subtracted by 3. So with an x value, and I've given you the x values here, I want you to notice where I'm getting them from as I'm adding 3 to these numbers here. So -1 plugged in here would give me f, and I'll just show the work for a couple of these, of -1 minus 3, because I'm replacing x right here with -1. Well, that equals f of -4. But we know what f of -4 was. F of -4 was 0. And then f of 1 is going to be 1 minus 3. Well, that's f of -2. And we know what f of -2 is. We can look at the graph and see that it's 2. We can go back to our table and see that it's 2. Then f of 3 minus 3, well, that's going to be the same as f of 0, which is 4. F of 5 minus 3 is f of 2, and f of 2 is 2. F of 7 minus 3 is equal to f of 4, and f of 4 is 0. So when we plot these values, what we're going to see is that this graph has actually been moved to the right 3. Let's see here. 1, 2, 3 went to 4, 5 went to 2, and 7 went to 0. All right, so let me just bring up this graph. I have f right here. So what this is saying is that if we were to look at the graph, as I put in, As I subtract numbers, I'm actually shifting to the right. Notice how the domain moves with it, okay? If I add numbers, I'm going to move to the left. Okay? You can ignore these functions. I had to make these in a kind of a weird sort of way, and I have some other functions reserved for later. But right now, we're just looking at this graph of f, which is the only one that had showing. All right, so let's go and look at on the outside. Well, when I add to the outside, it moves up and down the way you would expect. And it turns out that in functions, what you do to the inside is very different effect than what you do to the outside. So when I add or subtract to the outside, I shift the graph up and down. When I add subtract on the inside, I shift it left and right. And on the inside is opposite of what you say. We have a tradition here at Rockport High School of saying insiders lie. So when you see that a number is on the inside, it lies. You think a +4 might move it to the right, but it doesn't. It lies and moves it to the left. And we're going to see that pattern continue throughout. There's no mathematical justification there. The mathematical reason why it moves is because of the fact that it is happening before it enters the input. But the easy way to remember is that insiders lie. All right, let's go back and let's work another one of these transformations. Okay, on your note page, if you're following along on the paper, I did attach just another copy of f of x there for you to make that easier to look at, I think. So you're not flipping back and forth. You could also add the table of values if you want, but I've got them both here for us. All right, let's take a look at this one. Oh, hold on. Couldn't quite see the equation there. There we go. All right, this time we're going to be looking at 2 times f of x. So I'm going to take each one of these f of x values. The x's are the same. And I'm just going to multiply them by 2. So this will be 2 times 0, 2 times 2. So I'm multiplying the f of x times 2, the y value times 2. This will be an 8. This will be a 4, and this will be a 0. So the zeros, they didn't move, right? They did not move. But the other numbers were doubled. All right, and that gives us that kind of shape there. So what I want you to notice is that it's definitely steeper, much steeper. It has been stretched vertically, is what we say. The vertical expansion, you might hear it being said, but it's a vertical stretch when we multiply the f of x by that value. Well, let's see what happens when we do it to the inside. We've already talked about insiders lying. We've talked about insiders being affecting horizontally. So we're expecting that pattern to continue somehow. All right. Well, once again, you see I've had to change the x's to have it match the table because I'm taking the x's and multiplying by 2 before I go into the function. So, and again, I'm going to do some scratch work here on the side. F of 2x when x is -2 means f of 2 times -2. And I need to do that before, because I have to do everything in parentheses first. I have to do that before I evaluate. And so what that ends up becoming, even though I have x of -2, it ends up behaving like the -4 of the original function. So it's going to go to 0. And then when I use f of -1, when I use x equals -1, I have to find f of -2. And we know that that is 2. And when I find f of 0, 0 times 2 is, well, that's still f of 0. So that value is not going to change. That's just going to be 0, 4. All right, and then on the next one, I've got f of, I got to multiply 2 times the x, so 2 times 1 first. Well, that's f of 2. And we know that from the table over here, f of 2 is 2. Notice these y values are not changing. All right, f of 2, it needs to multiply by 2 before we evaluate those, so it's f of 4. So that 2 in front of the x, it causes us to multiply all the x's before we actually get to find the function value. All right, let's graph and see what this looks like. So we have a -2, 0, -1, 2, 0, 4, 1, 2, and 2, 0. So it did affect it horizontally, and it's hard to tell because the scaling's a little different. But can you see how it's been compressed horizontally? So earlier when we put in part C, we put the 2 on the outside, it got bigger vertically. But when we do it on the inside, it got smaller and horizontally. Let's take a look again, see if we can explore it again on Desmos. So if here's my f of x, my standard f of x. If I multiply it by 2 on the outside, you could see, oh yeah, it definitely stretched there, right? I could do 3. Making it bigger. What about like 0.5, 0.2? So these are all vertical changes, right? But if I put it on the inside, it ends up being compressed horizontally, and I can make that even more, right? I could also stretch it by making it 0.5, or you could call it 1/2, right? So when you put a number that's smaller on the inside, then it becomes to expand it horizontally. So you want to keep that in mind as well. All right, so let's take a look at another one. We just keep looking at all these different ways of changing it. Okay, I've got negative f of x. So what's going to happen here is that we're going to evaluate the function just like normal, but then when we get the output has to be multiplied by a -1. So 0, that's not going to change. That's just -0. But that becomes a -2, a -4, a -2, and a 0. So when I graph it, it's going to flip down here, isn't it? But some of you already knew that was going to happen, huh? So yeah, that flipped it over the x-axis. So that begs the question, what happens when the negative is on the inside? Well, some things show up better than others. Let's take a look. So we're going to plug in a -x on the inside. And so -4, let's do the scratch work again on the side here, because we have to do input. We got to work with that input before we find out what it is. So we're doing negative of -4. Got to do all that on the inside first. Well, negative of negative, that's a positive. So f of 4, I'm actually down here, y'all. That is 0. Then we got to do f of -2. So I'll do f of -2. Well, that's just f of 2, which is also 2. Okay. Now I got to do f of -0. Well, that's 0 is neither positive nor negative, so that's just a 4. Okay, next I got to do f of -2. Well, f of -2, that's not too hard to simplify. It's already done. F of -2 is 2. And lastly, I have to do f of -4, which is 0. And we plot the points. -4 went to 0. -2 went to 2. 0 went to 4. 2 went to 2. And 4 went to 0. Well, it's the same, isn't it? So do we think putting a negative inside causes no change in the function? No, I bet you didn't think that was true, right? Well, if you may have noticed that it's the same, but we kind of graphed it backwards, right? Because we were getting these values from over here on the right and mapping to the left. This function here has what we call y-axis symmetry. So functions that have y-axis symmetry, when you plug a -x into them, will result in having the same equation or same graph. So just something to think about there. That not always does a change affect something if it's because it could have symmetry. All right, now your next goal is to complete something pretty similar, but with a different function. So there's the function I want you to use. I want you to complete. You've got, I want to say quite a bit of them to do. So if you're following along notes, go ahead and go through them now. Pause the video, try your best, and then we will go over them and compare our answers. Okay, let's see how you did. First of all, you should fill in this table here. -6 went to -4. -5 goes to, looks like 0. -4 went to 4. 0 went to 4. Oops, that should be a 4. Yeah, 4 goes to 0. All right, so let's go through that and graph that. All right, let's see how you did. We got f of x minus 3 for the y values here. So I'm going to subtract 3 from each of these y values from over here in this f of x. So that'd be -3, and then 1, and then 1, and then -3. So I've got -7 at -6. Oh, that's way down here. And I've got -5 goes to -3. 4 goes to -1, 0 goes, 4 goes to 1, sorry. It's like this, right? Then 0 goes to 1, and then 4 goes to -3. All right, let's check it out. Let's explore that using our graphing calculator. So I'm just going to turn this function off, and this should be the function that you're looking at now, which I call g. So I have to change my letter here. And so we were doing f of x minus 3. So for our labeling here, it'd be g of x minus 3. And you can see that it certainly did shift it down, right? You can see now that I'm adding values and just continuing to move it up higher and higher and higher. Okay, so that makes sense. That's the way we expect it to be. Numbers on the outside should be making a vertical change, and they should be the direction you think, because they're outsiders, not insiders. All right, well, here comes that insider again. You always got to be wary of them, because they like to mess with you. So this is f of x plus 2. Now, you may have struggled to come up with the x values here, but remember what the x plus 2 does. It shifts everything back to the side 2. So because of that, I'm actually going to subtract 2 from each of these x values. So -6 will be a -8. -5 will be a -7. -4 needs to be a -6. 0 needs to be a -2. And 4 needs to be a 2. And you might find that a little unusual, but just let's check and I'll show you why it works. I told you to take each of those x values and subtract 2 to them, because I'm about to add 2 to them before I evaluate them, putting them right back where they were. So that's why I had to subtract 2 to them. And f of -6 is -4, and I think you can imagine that all of these values are going to end up getting mapped to where they used to be, making our graph just simply scoot over 2 to the left. And so there's that insider's lie, moving it left and right. All right, let's take a look at the next one. Okay, for this one, you should have multiplied the outputs, multiplied the y by a half. So the x values here, the f of x on the inside is the same, so these are not going to change. We'll just leave the same ones here. And when I multiply the y coordinates by half, they're all going to get smaller. So -4 divided by 2, 0 divided by 2, 4 divided by 2, 4 divided by 2, 0 divided by 2. So I end up with negative 6 goes to negative 2, negative 5 goes to positive. Oh, oops, that's wrong. What did negative 5 go to? 0 divided by 2 is 0. There we go. Negative 5 went to 0. Negative 4 went to 2. Then 0 goes to 2. And then 4 goes to 0. Still has the same x-intercepts, but it's been shifted, it's been shrunk vertically. Let's take a look at that one. So you can see that effect there. And I can make them even smaller and smaller and smaller, but it's never going to change those x-intercepts. It's just getting more and more compressed vertically. All right. Next one. This time we got the half on the inside, so we know that the effect should be on horizontal. And that effect should be somehow opposite of what we think. We think a half would make something smaller, but we know this is actually going to make something bigger. Well, since I'm going to be dividing each of these x coordinates by 2, I need them to be twice as big before I do so. So I'm actually going to do the opposite. Instead of having each of those x values, I'm going to multiply them all by 2. So negative 5 times 2, negative 4 times 2, 0 times 2, and 4 times 2. And then when I plug them in, if you're curious how it's going to work, remember we have to multiply by half first before we evaluate the function. Well, that becomes f of 1/2 of negative 12 is negative 6, but the f of negative 6 is negative 4. So this is what's going to happen on each one of them. These are going to be negative 4, that's going to be 0, that's going to be 4, that's going to be 4, that's going to be 0. So I'm way over here. I actually don't have enough room to graph it. All the way up until negative 8 goes to 4. And then that goes all the way across. And then 8 goes to 0. So it's going to be, let's see here, negative 8. Let's see here, negative 9, 10, 11, 12. It's going to be way down here. So yeah, it definitely expanded it out quite a bit. All right, now in this next one, you should have taken the x values and kept them the same since we're not doing anything to the input. And then the y values we're going to flip. So if that's going to be a positive 4, that'll become a negative 4 and a negative 4 and 0. So we're going to see negative 6 is going to go to positive 4, negative 5 there, negative 4 goes to negative 4, 0 goes to negative 4, and 4 goes to 0. So this is a vertical flip down below. As opposed to on the second one, and we will get the see an effect this time. We did not last time because of the y-axis symmetry. You could also have other kinds of symmetry, but so far that's the only one we have seen. So this time I'm going to change all these x values first. 6, 5, 4, 0, negative 4. And then the f of x values will be negative 4, 0, 4, 4, 0. So 6 goes to negative 4. 5 goes to 0. 4 goes to 4. 0 goes to 4. And negative 4 goes to 0. So we see that the negative on the inside has been a horizontal flip, not a vertical one. And then you had a couple to put together. You had to kind of mix and match these kind of things, right? So let's take a look at what you did there. So in this one here, hopefully you realize that we're going to be moving the x coordinates to the left 3 because it's opposite. So this will be a negative 9. This will be a negative 8. This will be a negative 7. This will be a negative 3. And this will be a positive 2. And then the y coordinates are going to be shifted down by 2. So it'll be a negative 6, negative 2, 2, 2, negative 2. So negative 9, negative 6. I don't have that much room on my paper, but I think I can fit it if I go right here. And then I've got negative 8, negative 2, negative 7, negative 7, positive 2, negative 3, positive 2, and then 2, negative 2. So this is a rigid transformation. It did not change the shape at all. It just moved 3 to the left 3, and then down 2. All right, on this one, you should have kept all of the x values the same because we're not doing any change on the input. But we're going to double the y values and flip them. So it'll be negative 6, positive 8, negative 5, 0, negative 4, negative 8, and I'm going to just kind of rough it. I don't have quite enough room on where I snap that. And then it'll come back to 4. So it's a stretching vertically twice and flipping it because of the negative. Okay, now it's time to talk about absolute value. The distance a number is from 0 is called its absolute value. So we'll write that in. So practice evaluating these right quick. The absolute value of 24 is 24. The absolute value of negative 7 is just 7, because it is 7 units from 0. The absolute value of 9 minus 17, well, 9 minus 17 is a negative 8, and the absolute value of negative 8 is 8. The absolute value of 4 is 4, and the absolute value of 7 is 7, and 4 minus 7 is negative 3. So you see that the absolute value is going to make things a positive number because distance is always a positive value in math and science. Absolute value, really super important. And it does some very intriguing things to our graphs. So let's throw that into our conversation right now. So what I want you to do is to take this graph. I want you to fill in a table of values, and then I want you to try and figure out what it does when you take the absolute value of the outside f of x, or if you take the absolute value of x first. You might be surprised. So pause the video and do that, and then we'll go over it together. All right, are you ready to go? Let's do this. Okay, so absolute value of f of x means that all of the y values that I get for output have to be converted to absolute value, which is essentially going to make them positive. So the absolute, when x equals negative 6, this function you should have said goes to negative 3. At negative 3, you got 0. At 0, you should have gotten 3. At 3, we have also 3. And then at 7, we have 3. All right, so the absolute value of f of x. Well, f of negative 6 is negative 3. But now we got to take the absolute value of that, which is actually just 3, right? So you see that it's going to remove these negative signs. So this is 3. That's 0, and then this is 3, 3, and 3. So I have negative 6 goes to positive 3, but negative 3 went to 0. So all that curve that was down here has now been flipped over Then it's going to go up to 0, 3, and then just kind of stay level. So what did the absolute value on the outside do? It took what was here and flipped it over there. So everything below the x-axis gets flipped up on top, okay? All right, let's take a look at what happens now when the absolute value is on the inside. I would say that the effect that absolute value has, whether it's on the inside of the function with the x or the outside, is the biggest difference of all the different types of transformation. That's my opinion. I think it's really quite unique. So what is f of the absolute value of negative 6? Well, we have to take the absolute value of negative 6 first, so it becomes f of 6. So if I go over here to f of 6, you'll see it's not on my table, unfortunately, but I do have it right here. It's a 3. I was able to find it right there on my graph, right? Okay, then I have f of the absolute value of negative 3. Well, that's just f of 3. We do have that in our table. The absolute value of 0 is 0. We have that. The absolute value of 3 is still 3, so that's just a 3 as well. And the absolute, and then we got absolute value of 7 is 7, so that's just 3. So we end up with this thing where everything is flat. Now, don't misunderstand me. That's not what the absolute value on the inside does. It doesn't make things flat. But what it did was it took everything to the right of the y-axis, all of this, and it pastes it, it flips it over and makes a copy of it on this side, and then just destroys all that. It's remarkable, right? I mean, it's quite a difference, isn't it? All right, well, if you haven't yet done them, there are a couple more practice problems for you to do like this. So let's go ahead and try them, and pause the video if you haven't done them yet. But I'm going to go ahead and just go right on through. Okay, so we have 2 times the absolute value of f of x. So I'm going to take the x values and I'm going to leave them the same. We're not changing the input, are we? But we're going to take their absolute value of f of x. The absolute value of negative 3 is 3, and double it, 6. 0, and then 6, 6, and 6. So this will be negative 6 is 6, negative 3 is 0. So you're seeing we're getting that reflecting and stretching here. And what about when we have a negative with the absolute value? Well, this should take our answer that we had from before and flip it downwards. So let's take a look at that one, make sure we got that. Okay, so we have negative. I'm not changing the input. There's nothing inside the function. So that's all these x values here, we can use the same ones, can't we? So the absolute value of f of negative 6 is 3, but then I have to make it negative. And then the absolute value of 3 is 3, but make it negative. So just like we thought, this is indeed going to shift everything down to down here. So it's still that function we had before with everything from the bottom moved up, flipped upwards, but then after doing that, it's flipped down. Okay, let's see how well you can put all this together. I'm going to give you a graph in the next practice problems, kind of a funky looking one, and I want you to take that graph of f. Let me pull that over here on this side right quick while we talk about it. And I don't want you to have to make a table. I don't want a table of values. I want you to just take the graph and make the transformations that I'm asking you to do. So go ahead and give it a try. All right, let's see how you did. So I have f of x plus 1. So what is that going to do? What is he doing? It's on the inside, left and right. This is going to shift everything to the left 1. So I was hoping to see that you just took these points here and moved them all to the left. And I know it's kind of a weird looking thing, but that's it. Likewise, we can shift it downwards. Let's do that one. Take all of these points here and shift all their y coordinates down. So this point here at -3, just a hair short of 4, is going to go down to just a hair below 0. So it becomes something kind of like that. And then -1 used to go to 5. It's going to go to 1 now. 0 used to go up to 7. It's going to go to 3 now. And while 2 used to go to -1, 2 is now going to go to -5 all the way down here. All right, next you had the graph y is equal to f of 2x. Let's see how you did on that one. That should be a horizontal compression by a factor of 2. So all of my x values I'm going to divide by 2. So -2 is going to become -3.5. That -3 is going to become -1.5. So -1.5 right there. The -1 will become -0.5. And then the 0 will stay 0. So same stuff's happening, it's just happening quicker, right? Because it's been compressed. And then 2 divided by 2 is 1, so now it's going to be like this. That's your horizontal compression. Okay, then you got to deal with absolute value. Where was it, on the inside or the outside? It's on the inside. Okay, so that means everything gets thrown away on the left because all negative x values will now be made positive. So I'm not even going to look at the left. I'm just going to jump right to the right. 0 goes to 7. 2 goes to -1. That's the right-hand side. What about the left-hand side? An exact mirror image. So just like that. Oh, that one wasn't a very good drawing. Just like that. Okay. As promised, though, I do have a graph that we can look at here of f of x. I wanted to play with some of these things. Let's go through and do x minus b. And decimals is cool. It lets you have a slider. So you can see that sliding it left and right, and that's why I put a minus. Okay. I can do an A. And I make an A. A is going to stretch vertically. Notice how it doesn't move it left and right any. It just moves, it doesn't change the domain at all when I slide the A. So multiplying, what you multiply in front is just going to multiply it up and down, okay? Not going to widen it at all. All right, I can also include a value to multiply on the inside. I can do a C. Now we'll add that slider. Let me put it in order, though. Hold on. All right, I ought to be able to move this down some. There it is. Okay. So the C, what we should see here is the graph's domain changing. Well, it's kind of hard to understand if it's negative. Let me keep it positive. So, I'll just, there we go, 0 to 10. All right, so you can see that as I enlarge this number, it starts getting to be more and more tight, and that domain is getting smaller and smaller, the x values. When I'm at 1, it's absolutely perfect. And then as I start going to fractions, we'll see it getting wider and wider. But yes, I could also multiply by a negative number and flip it horizontally as well. We saw that with the negative x. And lastly, we can move things up and down. I'm going to just add that slider D. And you'll see me just moving it up and down. So those are basically the 4 different types of transformations that we looked at, including the absolute value. And so, if you can do this with any function at all. But I have some piecewise defined functions to use. But if you go here, you can get some pretty cool examples and start finding some transformations and transformation translation programs already set up for you. So explore that. Okay, well, you do have an exit ticket to finish kind of summarizing what you learned today, so make sure you do that. And until next time, take care.